Good morning. My name is Mohammad Shahabuddin from Jet Propulsion Laboratory in Pasadena. Today, for the 2022 Flight Software Workshop, I will be talking about NISAR um, deployment of the antenna, a software perspective. And let me share my screen. So as I said, the topic is the NISAR antenna deployment, the software perspective. So today I will be talking about a little bit about NISAR mission, the NISAR flight software in a nutshell, the deployment overview, what we are deploying about, the state chart autocoder that we have used to write the software, and the autonomous antenna deployment state chart. And then the conclusion, and many thanks to the flight software team, NISAR systems team, and the projects team that helped achieve this mission and this software development. So NISAR is a joint partnership effort between NASA and ISRO. The observatory, once launched, will be studying natural hazards and global environmental changes. It provides a global coverage of the Earth in every 12 days. There are two synthetic aperture radar SAR instruments that will provide the science operation. The NASA provides the L-band SAR and ISRO provides the S-band SAR. The L-SAR instrument includes a 12-meter deployable mesh reflector, and a 9-meter deployable boom. You can find more interesting facts and information about the NISAR mission on this website. So flight software in a nutshell, flight software architecture at NASA JPL has evolved over many years. It is a robust architecture that has provided many successful missions. So NISAR flight software provides capabilities such as non-volatile memory, file system, instrument interfaces, power switch interface, time service, um, uplink, command uplink, software upload service, and telemetry downlink, and fault engine, such as monitoring faults and response and providing responses to those faults. Prashant Pandian from JPL gave a presentation last year at this very forum, the 2021 Flight Software Workshop. You can find detailed information about NISAR flight software. So deployment overview, the antenna deployment overview. In this presentation, we describe the use of state charts for the autonomous deployment of NISAR's mesh reflector and bloom deployment. JPL provides a large, complex, deployable L-band SAR instrument. The system engineers describe the autonomous behavior using flowcharts, flow diagrams, tables, and then the software engineer takes that information and use state charts or other tools. In this case, the state chart basically to design it and show that a state chart is a one-to-one relationship between the flow diagram. JPL's state chart autocoder, auto-generated code is nothing new. It has been used for software implementation in many missions. State charts are fully integrated into NISAR flight software architecture. So a little bit more about the deployment overview. The radar antenna at the time of launch, it is in a stored position or configuration, and it goes from that configuration into a fully deployable configuration. It takes, once we launch it, it takes about a month or so to actually open the antenna. Overall, a very complex deployment, and involves many disciplines, but in this presentation, we focus only on the software handling of the autonomous process. Antenna deployment goes through many phases, as you can see from the picture below, but we're only going to be focusing on the last two phases, where it is unrestrained and goes into the bloom state, and then the fully deployable state. So major activities for reflector deployment is a reflector bloom. When the reflector restraint is released by firing pyros, it causes the reflector to open or bloom. Software senses a successful bloom by comparing major tension against expected threshold. A timer parameter defines the amount to be in this state. If a successful bloom is not detected within the allotted time, then the behavior is aborted. Reflector deployment. After a successful bloom, powered reflector deployment begins. Two reflector deployment motors are powered on, and motor direction is set. There are 3 tension blocks that guide powered deployment, and each block has its unique tension and a spooler rev count threshold that determines to move to the next block or abort the behavior. So the first 2 blocks are successfully completed when the spooler rev count threshold is met within the tension limit. The third block is successfully completed when the final tension threshold is met within a total number of expected spooler rev counts. If the check in any of the block fails, the behavior is aborted, and then the system the ground operation teams can look into the behavior, whether if it's a failure, then they go back and try to address the issues. So a little bit more about the subsystem. The reflector subsystem comprises of a secondary restraint, which is fired by the pyros, or unrestrained by the pyros. There are 2 drive assemblies, the reflector itself. Each of the drive assembly has a 1 motor, a 1 cable spooler, 2 potentiometers, and 2 spooling potentiometers. So flight software computes revolution counts based on readings from each of the potentiometer spoolers according to the algorithms. These rev counts, along with cable tension, determine the success or failure of each of the tension block, as mentioned earlier. So a little bit about JPL state chart AutoCoder. The state chart AutoCoder, we call it SCA, was developed at JPL, here at JPL. SCA is a tool that makes UML, the Unified Modeling Language, state charts as input in the form of an XMI, and generates the state machine code implementation in a variety of languages such as C, C++, and Python. The tool is designed to receive UML state charts created in Magic Draw, which is a computer-aided software engineering tool. SCA produced code is robust and has been successfully used in many flight projects such as SMAP, MSL, and InSight, and other missions. So the state chart AutoCoder provides template implementation of .c file where programmer provides the functionality of the state chart actions, behavior, guard condition. And then we also have a unit test framework for the state chart that is available to exercise the transitions, all the transitions. So here's it describes a little bit about a broad level of the information flow coming from system engineers to the software engineers to the implementation. So system engineers provide the description of the system or the behavior of the system in terms of flowcharts, tables, descriptions in Word documents, algorithms, so we gather, being software engineers, we gather information and try to put it in a magic draw state chart, which basically follows the flowcharts and show a one-to-one correlation. So the state charts, once we have built that in the human language in Magic Draw, then it goes through a state chart AutoCoder. That state chart AutoCoder provides C files, AutoCoded C files, and it also provides a kind of a shell or a template C files where the software engineer can then put the behavior in that file. So here's a process of state chart AutoCode generation tool that was being provided by the developers of the state chart. Many thanks to them. So here, as I said, I mean, we draw the state chart in a Magic Draw, a commercial tool that gives as an XMI file. The UML tool or the state chart coder tool takes the XMI format, reads the information, validates the model. If there's any issue with the model, it's going to abort the code generation. Otherwise, it writes the target of the state machine into .c files. So this is a very simplified version of the actual state chart that we have used. This is just so that it makes it simple to understand. We have removed a lot of detailed information from here. So as we enter into this state chart, we are in an idle state, and we remain into idle state, until we actually are launched, and the ground operation team is ready to do a deployment. They send a flight command deployment, which is, by the way, the color coding over here is the blue is the ground command, or flight command. The red is an indication of some kind of a fault, and the black or gray transition lines are all autonomous lines. So in this case, the ground operations team issues a command deployment. It goes into the state over here into a bloom state, where once it enters into this unrestrained state, it is going to fire the pyros and unrestrain the reflector. So once it's unrestrained, it goes into this bloom target state where it's basically sitting over there and looking and monitoring the tension. And as we achieve the tension, the required tension, it goes into the bloom target achieved. The bloom target achieved transition signal will be generated, and it'll go into power deploy. In case if there's a problem meeting the required tension, it's going to stay in this state till the timer expires or some other fault is detected, and it's going to go into this, an abort signal will be generated and it'll go back into the idle state. So considering everything went fine with the bloom state, we are now in a power deploy. We start the timer to be in this particular state for a duration of time. In case things don't work out, then it is going to do an abort after the timer expires. So so the first thing we do is the motor management, where we're setting up the motor. Remember, we said initially there are two assemblies. Each assembly has a motor. So there are two motors. We're going to turn the motor direction and turn on the power on, and everything is good. It goes into this block 1 stage. As I mentioned earlier, I mean, this whole antenna deployment is carried out in 3 stages: block 1 to block 2 and block 3. And each stage we're looking for a specific ref count and a specific tension. If in any of the block, if that thing is not met, then the operation is aborted. Otherwise, it goes into the next state and the next state. Otherwise, if there were some problems with the motor, it's going to go into block 2 stage because the motors were disabled or some other issue. Otherwise, it's going to go into the block 3 state. In any if in any of the blocks, if there's an error, the abort is generated and you go back into the idle state. If everything goes according to the plan, then the block 3 target is achieved and we have a successful antenna deployment. In case if so, it's going to be in this state for a period of time. So there's a fixed duration of time that we expect that the antenna to be deployed. If nothing happens, then again the timer that we started at the beginning is going to expire, and the abort signal is generated, and we go back into this state again. This is just a textual explanation of what I already described. As mentioned earlier, the deployment state chart has 3 main states: the idle or initial state, the bloom state, where the unrestraint of the reflector happens and we monitor the tension. Power deployment state is the state where the motors are managed, and we go through block 1, block 2, and block 3 substate machines, and at any point, if we can't meet the target ref counts and tension, then the operation is aborted. And once it's aborted, the ground operations team can evaluate the condition, and they can go back and try to recommend deployment and go through the states. So the state chart code follows NISAR flight software architecture. As I mentioned earlier, it's fully integrated into the flight software, NISAR flight software architecture. Modules communicate with each other via IPC calls, inter-process communication. All strength transition signals are coded as IPC call. All internal and external triggers are generated by implementation code. All flight command or deployment is an IPC call which generates a signal transition on the state diagram. Guard conditions at the state transition is implemented as functions returning Boolean. State transition effect is implemented as a behavior by the implementation code. State chart is invoked at any time a new cable tension reading or new ref card is generated by a single IPC call. So in conclusion, state charts have been successfully used in many missions at JPL NASA. The software is robust. In many cases, a one-to-one relationship can be established between the system and design and the state chart. Easy to make late design changes in a state chart because all you have to do is rerun the AutoCoder and achieve the changes. Otherwise, if everything is manually coded, it takes a lot of amount of time to redo that. I thank you very much for coming and attending the presentation. Thank you.